today's lesson is overhead line mechanical design. So in last lessons, we already know that how to select the conductor side, how to select the insulator, and the transmission line set, and the line span, and the force on the transmission line conductor we already calculated last week. And today's lesson is we will consider the transmission line pole design. So this is the transmission line tower. So this one, because the height is h, and this is the wind force. So wind force is Fw. The unit will be the Newton. Wind force is the force here. So when the force is put on this tower, and this one is the moment of inertia. So this tower will be rotating. So we can calculate the bending moment. Bending moment M is equal to Fw multiply h. The unit will be the Newton into meter. H is the height of the pole. So this is the wind force. Wind force is inserting on this pole. So this pole will be rotating. So this is the plate. So we put the pole at the plate here. So this one will be rotating. So bending moment we can calculate. Bending moment M equal to Fw multiply h. So this is bending moment on the pole. Okay, this is the wind bending moment. And this pole normally those that are pole here. Pole got the cross arm. Cross arm. On the cross arm now we attach the conductor. So this one is a top diameter is D1 and the bottom diameter is D2. D1 and D2 we attach, and those are this height is a height H. H is the height of that tower. And we attach the conductor here. So those are conductor. So conductor got the weight. So this is transmission line tower. We put the cross arm. So this is the tower height. So those are conductor we attach. So in this case, this tower is suffering the two force. One force is the wind force. Another one will be the conductor force. So we can calculate the total bending moment. Total bending moment is equal to bending moment caused by the wind force. Bending moment caused by wind on the pole. Plus bending moment caused by wind on conductor. So this is a two bending moment. Two bending moment are put on the disc pole. So this pole is suffering two bending moment. One bending moment is a wind is directly hitting the pole. So this wind is trying to rotate the pole. Similarly, those conductors are also subject to the air. So because of the air pressure, those are twisting also they are trying to twist the pole. So two poles are inserting on the pole. One will be the wind force, another will be the wind force on the conductor. So wind directly force on the pole plus wind force on the conductor, two force. This tower is subject to the two force. So we can calculate total bending moment equal to bending moment caused by wind on pole plus bending moment caused by wind on the conductor. Okay, so we also calculate the bending moment caused by wind on force. Bending moment caused by wind on pole So this equation, we can use the equation. This equation is wind pressure. Wind pressure Pascal multiply H square and the D1 by 6 plus D2 by 3. So this is D1 and D2 is here. So diameter 1 is D1, this is D2. So this is the bending moment caused by wind on board. We can calculate by this formula. And also, bending moment caused by wind force of conductor. We can also calculate bending moment caused by wind on conductor. So the equation will be there, wind pressure multiply the area of conductor subject to wind, the area of conductor subject to wind for the whole span. Multiply number of conductor. Multiply 8. So we can calculate this way. So bending moment caused by wind on conductor equal to wind pressure multiply the area of conductor subject to wind for the whole span and number of conductor multiply H. So this is as a two bending moment on the conductor. So this is the bending moment. This is 1, this is 2. So the bending moment will be there 1 plus 2. Then you can call the total bending moment. So this is formula to calculate the total bending moment. Okay, so this total bending moment you can represent by M. M is the total bending moment. Then we can calculate the stress in the conductor. Another will be the maximum fiber stress. So this both are made of the fiber. Then with the timber. Timber is also the fiber stress on the concrete. Timber on the concrete they are made of. So this fiber stress you can calculate. F is equal to A multiply C by I. So this equation, F is fiber stress. F equal to maximum fiber stress. Unit with the Newton per meter square, M is the total bending moment. So Newton meter and C. So I is the moment of inertia. C means that, for example, you are made of the conductor in this way. So this is the pole. Pole is a circular pole. We usually make a circular shape. In this case, this one is the diameter D. So half of the diameter is C. In this case, C equal to T by 2. So we can use that T is the diameter. Diameter of circular pole. So we can put the C here. And the I is the moment of inertia. I equal to moment of inertia. Of circular pole. So I you can calculate. The formula is pi D4 by 64. So I is the moment of inertia. I calculate pi D4 by 64. And C is diameter of pole divided by 2. So by solving it, we substitute a formula, we can calculate the stress. So this stress is a pole stress. So this stress will be there compared with the standard pole. So we use as a timber. They are the timber. There are different kind of timber, concrete, the iron, So those ions got the allowable stress. So we compare with the aqueous stress and the allowable stress in the specification, and then we can select the appropriate pole. So then, based on this one, we calculate the stress. Based on above formula, we calculate the stress. We can calculate the stress in the pole. Then use the specification data to select the appropriate pole. So this is the thing. So based on above formula, we can calculate the stress on pole, then use the specification data to select the appropriate material for the pole. So this is a typical tower design. Tower design means this tower mechanical design. This tower subject to the wind force, also they are connected to a conductor. So we are putting on the conductor. So total bending moment is bending moment caused by wind force on pole plus bending moment caused by wind on the conductor. So wind force we can calculate by this formula, but for the conductor we can calculate by this formula. And then we add, you got the total bending moment. The total bending moment is N. And you also consider the shape of the pole. Pole is a circular shape. In this case, C is equal to D by 2. I is a moment of inertia. Moment of inertia of the circular pole is pi d 4 by 64. Then we substitute everything here, and we can calculate the stress. This stress is an actual stress suffered by the pole. So this stress table you can compare with the standard material specification. All material got a specific specification. The different timber got a different stress, and then we can set the appropriate material for the pole. So this is typical mechanical design for the tower pole. Okay, today's lesson is overhead line mechanical design. So